Hi all, welcome back. Alright, today we're going to start on talking about search. So learning objectives today, at the end of the day we should be able to define a directed graph and represent a problem as a state space graph, because that's what we're going to look at in here. Alright, so here's what we're going to do. We're going to start off this course with searching. And the idea here is that often we're not given an algorithm to solve, we're only a specification of what is a solution. We have to search for a solution. So we're going to have lots of cases about where specified what we have to solve, but not how to solve it, and we're going to search for a solution. So here's a typical problem. The agent's in one state, it has a set of deterministic actions it can carry out and wants to get to a goal state. A typical example of this is path planning, for example in Google Maps. You know, they assume that the agent, the person is at one particular location and can turn left, right or go straight and has to get to their destination. And so what we're going to do is we're going to abstract this problem into finding a path and directed graph, and we're going to map lots of other problems into this same problem so that way we can use the same techniques all the time. So what we're going to do is we're going to define a directed graph, we're going to map problems into that directed graph, and then we're going to work out different ways of solving path finding in directed graphs. That's how we're going to solve a number of different problems. And often there's more than one way to represent a problem as a graph. That's what we're going to look at today. So in terms of the dimensions before, we're going to look at a flat system. So we're going to just look at the one level abstraction. We're going to talk about explicit states. What are the states that we have to look at? We're not going to reason about features or individuals and relations. We're going to look at an indefinite stage. We don't know how many steps it's going to take to get there. We're assuming it's fully observable, deterministic, with goals, with a single agent, knowledge is given, and personal rationality. And these are often assumptions that we're going to make just to keep things simple. Okay, so here's the state space problem. There's a set of states and a subset of states called the start states. So we have just a set of states and a set of start states and a set of actions. And what we also need then is a action function. Given in a state and an action, it returns a new state. So this is assuming that we have a deterministic system. So that's why we can do this. Then we have a set of goal states. I'm going to specify this as a function, the goal of S, where goal of S is true if S is a goal state. And we're going to have a criterion that specifies the quality of an acceptable solution. So let's look at one example of this. An obvious example of this is when we go, look at Google Maps. So here's the Google Maps thing. I want to find a path here. The states, we'll talk about what the states are, but here we're trying to get from work, which is in the computer science building, and suppose we want to get to Stanley Park Brewing Restaurant and State. So that's what our goal is to get through here. The start state is the computer science building, the goal state is the Stanley Park Brewing. And there are a whole lot of different solutions, and it's going to come along with one path. It's going to tell us how to actually get from the computer science building to Stanley Park. So there's a number of different ways we can get through this, and this is going to be the fit to our system. So we're essentially going to assume it's deterministic. We're essentially not going to plan on, it's going to give you a whole lot of routes we're going to do, and we're not planning on changing our minds. That's also why it's sort of offline. So we're going to find a route, commit to that route, and then follow that route all the way till the end. So they've abstracted this into a deterministic system that's fully observable, and that's what we're going to assume here. Okay, so this is a sort of classic example of how this is going to work. All right. So here's another example of this. So we're going to have a delivery robot, and this is the domain we're going to use. So a robot wants to get from outside room 103 to inside of room 123. So it wants to get from, so what we're going to do is to label all of the locations with names. And here we've named some of them. So 0123 is the outside of room 123. All these other parts are rooms in here. And so what we're going to do is to try to find out which way we can get to there, and assume that these doors here, robot can only push them, so it can go from 0103 to B3 but not backwards. So it's going to work out how to get to route to here. So here's a typical problem, and of course it wants to try to travel straight for it, and then it gets stuck. So it's got to try and find out how it's going to do this, and we're assuming that it has a map. So assuming the system It's fully observable. Okay, so what we're going to do is we're going to abstract this problem into a directed graph. Some of you have seen a directed graph before. So a directed graph consists of a set of nodes and a set of ordered pairs of nodes called arcs. So there's just a set of nodes and a set of ordered pairs of nodes called arcs. So we're going to say node n2 is a neighbour of n1 if there's an arc from n1 to n2. That is, if this ordered pair is the set of all of the arcs. n1, n2 is a set of all the arcs. So a path is then a sequence of nodes such that there's an arc between n1 and n2, an arc between n1 and n2, an arc between n2 and n3, etc. So in other words, if there's a path between ni minus 1 and ni is an arc. Because that's what it's going to path is. So it's any sequence of nodes where each pair of them is an arc. Okay, so given a set of start nodes and a set of goal nodes, a solution is a path from a start node to a goal node. So we're going to talk about just finding a solution to a graph searching problem. And often we can have costs associated with arcs. The cost of a path is the sum of the costs of the arcs in the path. So the cost of this is just the sum of all the costs of the arcs. So an optimal solution is one with minimum cost. And in Google Maps, the cost is the time it's going, so I to estimate the time it takes to traverse this, and that's what it's trying to optimize. It's trying to optimize the time to get from the start location to the ending location. So what's a state? So it might think that a state's obvious, but it's not. So usually when we design a problem, we have to carefully design what is a state. So it turns out that the state needs to include enough information to determine what is the next state. So if you're in a state, you should be able to determine what's the next state. So that's part of it to make sure that we can do this. It has enough information to do this. It needs to determine whether the goal is achieved. So you need to know, have I reached the goal or not? That's also part of the state. The other one is to determine the cost of the path. So the state needs enough information to do these three things. So here's an example. And often there are lots of options to keep in the state. And we want to keep the states as simple as possible, but no simpler. We don't want to oversimplify things because then we can't keep track of the information that we need. So here's an example of this problem for a delivery robot. So we've decided to give names to all of these locations, and then we're going to draw a graph of how you can get from one to another. And let's suppose we only include the bolded locations in here, and we get to a graph like that. So we can get from 0103 to 0109, and 0103 to B3, and 0103 to the top of the stairs. So you get from 0103 to B3, 0103 to 0109, 0103 to the top of the stairs. For 0109, suppose we can get to 0111 or to 0119. Okay, so that's what we're going to map here. So this is this graph here, and we're assuming we have costs associated with this. So it's a typical one here where the states are enough to have, it's enough just to have the location as the state. If you look at Google Maps, it turns out, if you look at Google Maps again, it turns out that it's not enough information to determine the location is not enough. So the nodes, you might think the nodes are just these points, but that's not enough information to determine the cost because turning left and going straight has a very different cost. So in Google Maps, the state is both the location, which is the intersection, and the direction that the agent's traveling in. And that gives enough information to determine which way to go and whether to get there, and also determine the costs. So we need both the intersection and the direction that the driver is traveling. And that's how we're going to end up with a map like this. If you're walking, you don't need to worry about the direction that they're going in. We can ignore that. But for driving, the cost, the time, depends on which way you turn. If it was the distance, we wouldn't need it either. So that's why we're going to the cost. What the state is becomes important. Okay, so that's Google Maps. So there's single start location and goal location. So there's only a single start location, a single goal location. The cost is the estimated time, and Google spends a lot of its effort in the maps section to actually estimate the time accurately. but you don't get a choice. You can't say, I'd rather see a scenic route than minimize time. Google doesn't provide that. It's a built-in utility function, and you have to follow what Google wants you to do, and that's minimize time. And the state here needs to include the direction because the cost depends on directions. So the state here needs to depend on both the intersection and the directions. For example, turning left in here. And so that's what's going to happen here, is we need to think about what we need in the state. So here's another example. Suppose we have a video game, and this robot Rob is on a grid, so it can go up, down, left, right, and needs to collect some coins, C1, C2, C3, C4. It's not without running out of fuel, and it's got to end up in location 1, 1. So in this example here, Rob is at location 5, 8. If Rob visits this location C3 at position 5, 7, it collects coin C3. And that's what that means. If Rob ends up at this location 4, 9 where there's a fuel, it can refill. And every time it steps, it reduces the amount of fuel it has. So there's a typical example here. So in here, the state in here has to include where Rob is, because that's important for knowing what's happening. So it has to determine whether, where the robot is part of the state in here. Another part of the state in here is how much fuel Rob has, because as Rob moves, we don't want the robot to run out of fuel. Okay, and it also has to keep track of what coins it has. So it has to keep track of, does it have coin 1, C1, does it have coin C2, does it have coin C3, does it have coin C4. It doesn't have to keep where you collect coins doesn't have to be part of the state space, because it's not going to be something that's going to change. It's not needed in order to be a state. Neither is the location of this. It's just part of the background knowledge. And the goal here is to get to a state where you're at position 1, 1, and C1 is true, whether you have C3, 2 is true, C3 is true, and C4 is true. But we don't care about the fuel. The fuel can be anything. And so if we think about this state, the graph from this one, we could have this location here is at now location 5. If you look at this one here, it's at location 5, 8. So Rob's at location 5, 8. It's got 6 units of fuel. It doesn't have coin C1. It does have coin C2. It does have coin C3. And it does have coin C4. So from here it can move up. And when it moves up, it ends up at position 5, 9 here. But it only has 5 units of fuel left. It still has the same coins it had before. If instead it moved down, it was at position 5, 7. It now has 5 units of fuel, but it now has coin C3. So this one here is now true. The third element here is true. And if it moves right, it still reduces the amount of fuel. When it goes up, when it's at position 5, 9, and it goes left, then it fills up with fuel. So maybe it can fill up with fuel. It gets 20 units of fuel. So this is how we could represent a video game in terms of a state space. Here's another example we can have. A robot cleaner. There are 2 rooms and 1 cleaning robot. The rooms can be clean or dirty. The robot actions can suck, make the room that the robot's in clean, or it can move to another room. So the robot can do 2 things. And the goal is to have both rooms clean. So how many states are there and what are they? So think about this before our class on Tuesday, and we'll discuss this and see what's happening. There's an interesting solution to this problem. Okay, thanks for listening.